Hi, welcome to this lecture on series solutions at ODEs. This will be our last topic, and it's just going to be brief. You're probably going to see just one problem at most in the final exam based on this topic, and that will be an extra credit problem. So consider this differential equation, 1 minus x squared times y double prime minus 2x times y prime plus 2y. This is called Legendre's equation, and it's important in math and physics because it appears when you solve the Laplacian. So if you're interested, you solve this Laplace's equation, it's equal to the second derivative of f with respect to x plus the second derivative of f with respect to y. If you solve that's equal to 0, if you solve this equation in polar coordinates r and theta, this equation will change, make the change of variables from x and y to r and theta. You'll get this for the angle theta. Theta actually will satisfy an equation that looks like this. And it's also appears when you solve Schrodinger's equation. So Schrodinger's equation will give you the equation if you try to solve Schrodinger's equation in two variables. In any case, point is this is important in physics and engineering, and because the coefficients are not constant. So what are the coefficients here? 1 minus x squared, 2x, and 2. Okay, 2 is constant, but 2x and 1 minus x squared, they're not constant. So we can't just use the characteristic polynomial approach for a higher order ODE. However, we can solve the equation using power series. And power series is very useful for solving linear ODEs. Not so much for nonlinear ODEs, but for linear ODEs it is. So let's recall what a power series is. A power series is a way to express a function as an infinite sum. F of x is equal to the sum from n is equal to 0 to positive infinity of an times x to the n. Now, an are constants, x is of course the variable. So you want to think of this, okay, so what is this really saying? This is the limit, right, as n goes to positive infinity of this sum. 0 plus a1x plus a2 x squared, etc., all the way up to a and xn. So it's a limit of polynomials. Now, by the ratio test, this series is going to converge only if the limit as n goes to positive infinity of the absolute value of an plus 1 times x to n plus 1 over an times x to n is less than 0. Now, x to the n plus 1 over x to n, this just becomes x, right? N plus 1 minus n is equal to 1, so we're left with x to the first power over x, and we're multiplying by the absolute value of a sub n plus 1 over a sub n. So we're left with, when n goes to infinity, absolute value of an plus 1 over an times absolute value of x. This is less than 1, and it will converge if that's true. If it's equal to 1, the ratio test doesn't really say anything. So it's possible that this power series could converge at x equal to when this limit is equal to 1, but when it's less than 1, we're guaranteed convergence. Now, if you rewrite this equation, notice absolute of x, this does not depend upon n, so it's not going to affect the limit. You can factor this absolute value of x out, and then divide both sides by limit n goes to infinity of absolute value of an plus 1 over an, provided it's non-zero. And the series is going to converge if, so when you bring this over to the right-hand side, what you're left with is the absolute value of x, and you're left with on the right-hand side 1 over, and then n goes to infinity, absolute value of an plus 1 over an. Now, this number here on the right-hand side is called the radius of convergence. And what this means is that when absolute value of x is less than this number, the series will converge. So this will actually give you an interval from on a real number line from minus r to positive r. 0 is going to be right here in center. Now, okay, so that's a series expansion about 0. Let's call it. You can also do series expansion about another number. Let's concentrate on 0 for now. That will simplify things. If it's not around 0, you can usually kind of shift things over to 0. So, but the ideas really do remain the same. If we set y, an unknown function, to be an unknown power series, so here that means x to the n, okay, that's a known function, but an is unknown. What happens when you start differentiating? Well, notice this infinite sum is a limit of polynomials. So it turns out that when you differentiate, you can just differentiate term by term. But differentiate polynomials is really straightforward. You just you leave an alone, bring the exponent down, and subtract 1. It's just the power rule. N times an times x to the n minus 1. Power rule again, you get y double prime is n times n minus 1 times x to n minus 2. Now notice here, it's useful to write this from n equal to 0 to infinity. And notice when n is 0, this term is n times 0 times an, 0 times a0 is just 0. So we do start when n is equal to 1. That means all the terms here are going to be coefficients of x to the 0 or above. You're not going to have any terms that are 1 over x. Okay. Y double prime, n times n minus 1 times x to n minus 2. Well, n times n minus 1 times x to n minus 2. This is 0 when n is 0. It's also 0 when n is 1. So that means we start when n is equal to 2. And again, this term here is x to the n minus 2. So all our terms look like x to the 0 and above. X to the 0, x to the first, and above. So these y prime and y double prime are also power series. Now let's see how this plays out. And I think it's best seen in an example. How do we use Legendre's equation how do we use power series to solve Legendre's equation? Well, let's plug in y double prime, the formula for y double prime as a power series to the first term. 1 minus x squared y double prime is equal to 1 minus x squared times this infinite sum. Now, because this is a limit of polynomials, it turns out we can just bring this x squared inside the summand. We can also bring 1 inside the summand and just subtract, provided both series converge. Multiplying by x squared, what do we get? We get n times n minus 1 times x to the n. Here's n minus 2. N minus x to the n minus 2 times x squared is equal to x to the n minus 2 plus 2, just from laws of exponents. So we're left with an times x to the n. Now, multiply by 1. What happens when we multiply by 1? Well, when we multiply by 1, what ends up happening is we get, so this should have been an n, but n is a dummy variable because it doesn't matter what you call it, right? So it's n. So, okay, so this first term really should have just been n times n minus 1 times a sub n times x raised to the n minus 2 power. Now when you set m equal to n minus 2, n is equal to n plus 2, and n minus 1 is equal to n plus 1. That's why we're left with this, a sub n plus 2. So this first sum becomes n plus 2 times n plus 1 times a sub n plus 2 times x to the n. Why are we doing that? We're doing that so that we can combine the two power series into one. And we collect like terms. These are our coefficients x to n. If we replace n here with m, because n is just a dummy variable, these are also coefficients of x to the n. So what are we left with? So notice that's the reason in this sum we had to change n to, we had to replace n minus 2 with m so that the exponent would be x to the n, not x to the n minus 2. So it's a like term to what we see in the second series. N plus 2 times n plus 1 times a sub n plus 2 minus m times n plus minus 1 times am. N plus 2, n plus 1, a sub n plus 2 minus m times n minus 1 times am, all times x to n. So one power series, bunch of terms inside the summand and as coefficients of x to n. Let's look at the next terms. Negative 2xy prime. Okay, so now n y prime was n times a n times x to the minus 1. Multiply this by negative 2x, you just get negative 2n times a n times x to n. Again, we convert everything to m because that's what we used to index the previous sum, the summand for the first term. And same thing for 2y. So 2y, just bring the 2 inside of the summand, replace n with m. Again, that's just so we can combine it with the first series that we computed. Now let's solve, but let's combine all these terms together. 1 minus x squared times y double prime minus 2x times y prime plus 2y. This first term was m plus 2 times m plus 1 times a sub m plus 2 minus m times m minus 1 times am times x to n. Now we subtract, or add, negative 2m am x to the m, this sum, and we add 2am x to n. So you see we have x to n here, x to n, x to n. We can just combine all these terms together now. So pull out x to combine the summands, put these two terms in the summand, pull out the x to n, and then add negative 2m am and 2am in the coefficient of x to n. Now when we do that, we also need to worry about terms involving an plus 2 and terms involving am. What's a term involving an plus 2? An plus 2 times n plus 2 times n plus 1. This is the only term that involves an plus 2. What are the terms that involve an? There's this term, negative m times m minus 1. There's this term, negative 2an. And there's this term, 2an. Factoring am out of all those terms leaves negative m times m minus 1 minus 2m plus 2. Negative m squared. So this becomes negative m squared plus m minus 2m, which is the same as negative m squared plus m plus 2. So these are all the terms that involve am. This is a term that just involves a sub n plus 2. When we write this in terms of series, Legendre's equation then becomes the following. So this is from putting everything inside the summand, pulling x to the m out, combining terms that involve am plus 2, and combining like terms that have am as a factor. If this is 0, that means each term, just like a polynomial, each term individually has to be 0. In particular, the coefficient of every single x to the n from m equal to 0 to m equal to positive infinity has to be 0. So it will be 0 only if each term is 0, which means we put each coefficient of x to the n equal to 0. Now, we can solve this as a recursive relation for a sub n plus 2 in terms of an. We add m squared plus m minus 2 to both sides. We get m squared plus m minus 2 over m plus 2 times m plus 1 times an. That's just adding this term to both sides, dividing through by m plus 2 times m plus 1. If a1 is 1, we get a3 is 0, and subsequently an is 0 for all odd n. That means y1 of x is equal to x is one solution. This is called the Legendre formula. So that's a pretty simple solution. So what you can think, okay, well, why do we need to use series? Well, okay, it's possible. You could have just, say, sort of guessed that your solution would have the form y1 of x is equal to, say, a times x. But again, that's a lucky guess. And if the equation changes slightly, if 2 here is replaced with, say, n times n plus 1, this series technique will always work to give a recursive relation for the coefficients of y1 of x. And this y1 of x is going to be a Legendre polynomial. And depending upon whether or not n in the formula for n times n plus 1 is even or odd, it will be either an even polynomial or an odd polynomial. That is, an even degree polynomial or an odd degree polynomial. And this, so it is and we can solve for the coefficients just from the recursive relation. This is important. These polynomials appear quite often, especially in solutions to Schrodinger's equation and quantum mechanics. Now let's say instead of saying a1 was 1, let's say a naught was 1. And what do we get? A2 is negative 1. A4 is negative a third. A6 is negative 1/5. So what does this look like? We have 1, negative 1, negative a third, negative 1/5. Well, it looks like, okay, 1, negative 1, this is positive, but all these other terms are negative, so it's not, unfortunately, it's not an alternating series. And we are dividing by the next odd number, first dividing by 1, then dividing by 3, then dividing by 5. And y2 then, we try to construct a second solution, second linearly independent solution. 1 minus x squared minus x Well, this should have been x cubed. X cubed over 3. This should have been an x to the 4th, and this should have been x to the 6th. But either way, what's important is not how these coefficients, 1/3 and 1/5, they're very similar to the harmonic series. Instead of just increasing by 1 each time, you're just counting and increasing by 2, but with the odd numbers. But the problem is harmonic series do not converge. And it turns out this series ends up diverging. So Legendre polynomial is the only one that's obtained with the series method. So yes, the series method is not complete, especially in this case, because it only gives one linearly independent solution. There's more than one. There's a theorem that says that any second degree linear ODE, whose coefficients are reasonable functions of x, in this case they are because polynomials, will always have two linearly independent solutions. So you might think to yourself, where's the other one? Well, there is another one, but that cannot be obtained via the series method. Actually can be obtained via the series method, but you have to use not power series, but what's called a Lorentz series, and that's in 1 over x. So that series will have a singularity at x equal to 0 and x equal to 1. So if you're welcome to look that up online, but you're not going to be testing that, which you could be tested on, as again, like I said, just an extra credit problem will be the series method. So again, we have this one solution, and series methods can be obtained. We're not always going to get polynomials. You can indeed solve and just get series. So if this series ended up converging, and there are other examples of differential equations where what you get here, let's say this was -1, -1 over 3 squared, -1 over 5 squared, well, that would converge, provided obviously that x is less than positive infinity, then you wouldn't get a second solution. And this would be something like sine or cosine, or maybe some similar function. But there's also functions that just are defined literally by power series and cannot be expressed in closed form, either as polynomials or as sine or cosine. Okay, so that's it for the power series method. Again, what's most important is the method, not so much the fact that we just got a polynomial at the very end. Okay, and like I said again, you're going to see one problem on the final exam that's an extra credit problem based on this method. Best wishes for the final.